Alrighty, today we're going to talk about Unit 8.1. We are going to learn how to integrate absolute values, and we're going to do a little bit of review to PVA. This is going to help us move into 8.2 and 8.3, where we're going to talk about integration involving area and volume. First thing we're going to do is figure out how do we integrate absolute values. Very easy, we've got 4 different steps. Step 1, we're going to find our zeros, basically eliminate the absolutes, make our equations positive. To do this, we're probably going to have to rearrange. Then we determine our antiderivative, take the integral, and finally we evaluate it using the fundamental theorem of calculus, our FTC. So let's look at an example problem. We have the integral from 0 to 5 of the absolute value of x minus 4. So let's do step 1. Let's go ahead and eliminate those zeros. So let's start with our absolute value of x minus 4. Right now, we're looking at an interval from 0 to 5. But what happens when we set it to 0? Then that means x equals 4, which means I now have new intervals from 0 to 4 and from 4 to 5. So we're going to look at those and we're going to figure out some information. So there's our new interval from 0 to 4. But what equation am I going to put here that's going to make every value positive in my function on the interval from 0 to 4? Well, right now, if I plug it in, it's not going to be positive inherently if I drop the absolute values. If I put x minus 4 here, and I plugged in any value in between, let's say 0. I put 0 minus 4, it's going to be a negative value. That's not what we want. We want a positive value. So what can I do to this to make that a positive value? Well, usually, we're just adding a negative somewhere. In this instance, if I make the x a negative, just the x by itself, well, plug that 0 back in. Okay, 0, negative 4, it's still negative. That's wrong. What if I change just this one? Maybe, but we really can't do just an individual one. So what I'm going to do is I'm going to multiply the entire thing by negative 1. And we're going to distribute that, of course. So what does that look like? It becomes negative x plus 4. And think about it. When I plug in any value in this interval, this will be a positive function. What about our next interval? From 4 to 5. Cool. Again, I need, without absolutes, I need some form of this function. Well, let's test the original function, x minus 4. If I plug in 4, 0, that's neutral, positive I suppose. 5 minus 4 is 1. Hey, that's positive. That means I'm using my regular equation. Let's move on to step 2. Okay, let's go ahead and rearrange our integral. Originally it went from 0 to 5 of the absolute value of x minus 4. Well, let's pull it apart. My new interval from 0 to 4 of this new function. My new interval from 4 to 5 of its new function. What do we call this? This is called additivity. I can split apart my original interval. I can definitely do that. We're allowed to do that. Let's move on to step 3. Now we have to actually evaluate this integral. So very quickly, I wrote out those evaluation steps. I used my sum and difference property of my my integrals right here. I separated them out. Oh no, wait, they're already separated, sorry. I meant right here. We could separate them right there. But then we're going to evaluate them from 0 to 4 and from 4 to 5. So let's see that. So now I'm going to evaluate from 4 to 0 and 5 to 4. What is this called? This is our fundamental theorem of calculus, is it not? B minus A, B minus A. So I plug in those values and we get our answer of 17 over 2. Let's do one more example. Same thing. So step 1, let's eliminate those zeros. So there's our original 2x minus 1. There's our original interval. So let's get rid of those absolutes. And what are we looking at? First things first, let's go ahead and solve it. So then x must be equal to 1/2. So I have new intervals from 0 to 1/2 and from 1/2 to 2. We see that? We split apart our intervals. So let's look at that first interval from 0 to 1/2. Okay, let's plug in a value. If I plug in 0, then I'm going to be left with negative 1. That's negative. If I pull out those absolutes, it's going to be negative. We don't want that. So let's try putting a negative in front of it. What happens if I put a negative in front of it? Well, that becomes negative 2x plus 1 If I plug in 0, that makes it positive. That's probably going to be what we want to see. And look at that, it is. Again, we like to distribute that negative. I forgot to do it here, but I did it later. Now we're going to look at our second interval. So let's plug in a value. Let's plug in 2. This becomes 4 minus 1. That's a positive value. Let's plug in this one. 2 times 1/2. 1 minus 1 is 0. Neutral, but it's still not negative. So that means we're going to use our original equation. Step 2, let's rearrange our integral. Here's my original integral, and we're going to use additivity to pull it apart. My new interval with my new function. Here I already distributed the negative. My new interval with my new function. Step 3, let's evaluate that integral. Went ahead and evaluated it. Got my evaluation signs. And then finally, step 4, we're going to apply our fundamental theorem of calculus, get some funky fractions, and we get an answer of 5/2. All right, moving forward, let's go on to reviewing our position, velocity, and acceleration. Some of these will be old slides that you've seen before, but really we just need to be talking about these very briefly, very quickly. So, we know that position can be represented as s of t and as xt. Position is simply the function that gives is just an object as a function of time. It's just your particle along your x-axis or whatever relative to your origin. But what about velocity? So velocity can be represented as v of t, but velocity is going to be equivalent to the position's derivative, so s prime or x prime. But what is velocity? Because it's the derivative, that means that it must be change in position. I got distracted by myself. So velocity is the change in position. So when we hear those words, change in position, that's got to be my derivative. What else? If velocity is negative, we're going left or down in a negative direction. If velocity is positive, we're going right or up. What happens if velocity is 0? We are at rest. And finally, we're looking at acceleration. Acceleration is denoted by a of t. Acceleration is the derivative of velocity. It's also the second derivative of position. So both s double prime and x double prime, or v prime. And velocity is the change, acceleration is the change in velocity. So it must be its derivative. If acceleration and velocity have the same sign, then my speed is increasing. If acceleration and velocity have different signs, my speed is decreasing. Here's where I saw a lot of mistakes with you guys last semester. So I want you to know, whenever you see the word speed, we're not talking about velocity. Typically, we are talking about the relationship between acceleration and velocity. So if you hear the word speed, if you see the word speed, you should be looking for the relationship between velocity and acceleration, specifically their signs. Some graphical examples, you've seen these before, so let's run through them very quickly. Right now, this is the graph of my position. So this is s of t or x of t. This is the graph of my position. And it wants to know, when is p moving to the left, and why do we know that it's moving to the left? Well, if this is the graph of my position, then it must be moving to the left from 0 to 2 and from 7 to 9. Why? What's going on at 0 to 2 and 7 to 9? Oh wait, those are negative slopes. If my slope is negative, that means my derivative is negative. And what is the derivative of position? Velocity. So velocity is negative. That means I'm going left or down. Ta-da. When is P standing still?
Maureen Santibáñez, please come to the main office. Maureen Santibáñez, please report to the main office.
Sorry. So, when is position standing still? Okay, again, let's go back to what we know. Movement, left, right, standing still is not based off the position graph. It's based off the velocity graph. So now I have to look, where is the velocity equal to 0? Well, I'm looking at position. So where is my slope equal to 0? Right there and right there. So I've got a slope from 5 to 7 and 9 to 12. And there's our explanation. And finally, or not finally, next question, when is the first time that P reverses direction? So this is the first time I go from left to right or from right to left. Not necessarily standing still, left to right, right to left. So if I'm looking at position, then I need to know velocity went from negative to positive or positive to negative. So I have to know that the slope is going from negative to positive or positive to negative. Well, here is my first instance of a change in direction. And there's actually probably the only one. So P reverses direction at t equals 2 because its slope is going from negative to positive, or the function is going from decreasing to increasing. It's fine. Final question regarding position. When does P move at its greatest speed? Okay, so this is an interesting question. Now we're talking about speed. Speed is the relationship between velocity and acceleration, but we actually know that its greatest speed is going to be from 7 to 9. Why? Because this is the steepest slope. So if the graph of position, its steepest slope is going to be its greatest speed. Now we're looking at the graph of velocity. So if I'm looking at the graph of velocity, I'm basically looking at the graph of f prime. So I know that if any position questions, I'm thinking about f. Any acceleration questions, I'm thinking about f double prime. If I'm looking at velocity questions, I am looking at this graph. So when is P moving to the left? Previously, we looked for the slope being negative. But my slope previously was this graph. So I don't need to look for its slope being negative. I just need to know when the graph itself is negative, which is right there from like 8.3, 13.5. Next question, when is it standing still? Again, this is when velocity equals 0. Well, this is the graph of velocity, so where does it equal 0? Right there and right there. X-intercepts, roots, zeros. So at 8.3 and 13.5, when is the first time that P reverses direction? Again, same thing. My velocity has to go from negative to positive or from positive to negative. So my velocity is positive, 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 negative. That's my first instance. Right there at 8.3. And then when does P move at its greatest speed? Well, this one's different. Previously, we were looking at the graph of position. So its biggest slope was going to be its greatest speed. Here, we are actually looking at velocity. So its highest point is its greatest speed. So right there, 5 to 7, highest point. All right, so let's talk about a wrap-up. Oh, there was one more question, my bad. When does P speed up? Okay, here, speed. So now we have to think about the relationship between velocity and acceleration. For something to speed up, both velocity and acceleration have to have the same sign. They don't have to both be positive, they can both be negative, but they have to have the same sign. Same energy, both directions. Opposing energy or opposite signs would cause it to slow down. So when does it speed up? Well, this is where all velocity is positive, and this is where all velocity is negative. Well, what about acceleration? Acceleration is simply the derivative of velocity. So we're just looking at the slopes. So I have a negative slope but positive velocity. Now, positive slope and positive velocity, yeah, that's a spot right here. 0. Negative slope, positive velocity. No. Negative slope, negative velocity. Yes. Positive slope, negative, positive slope, positive. We're good there. So those are my instances where we would have something speeding up. Very good. And when does it slow down? Now we're looking for those opposing forces. So negative slope, positive velocity. Negative slope, positive velocity. Positive slope, negative velocity. Ta-da! Is that my last question? Yes. Okay, so let's talk about a wrap-up. We know that right now we're talking about position, velocity, acceleration is f prime, and f double prime. But now we've learned some new information. We've learned about our integral. And I've shown you before that we can relate those two. So I could technically relate my integral as my position, my velocity as my function, and my acceleration as f prime. We can see that relationship because they go in the same direction. This is to show you those to speed. This is a part that I think kids struggle with when they talk about speed slowing up and slowing down. They forget that it's a relationship. It isn't just velocity by itself. Sometimes it is, because velocity or speed is the absolute value, but velocity and acceleration have a relationship, and that's how we can really determine whether an object is slowing up, slowing down, speeding up. And finally, I have this list, and I'll read it out to you because I don't think you can see it on the video, but I'll read it out to you just to kind of get a general idea. When they're asking, these are questions for how you would see it in a test question, in a word problem. When they ask you initially, when you see the words initially, then you want t to equal 0, time to equal 0. When you see the words at rest, that means v of t equals 0. When you see the words at the origin, that means your position is equal to 0, which means x of t or s of t equals 0. When they say velocity is positive, that means your position, your particle is moving to the right or up. When your velocity is negative, your particle is moving to the left or down. When you're looking for average velocity, this is the change in position with respect to time divided by time. This is the like position minus position all over time minus time. So x of b minus x of a all over b minus a basically is what you're talking about. If you're looking for average velocity with relationship to velocity itself, this is the new information. The rest of this was old. This is the new information. Then you need to use the average value theorem, which we learned this unit, or last unit, the average value theorem, which is that 1 over b minus a just times my definite integral of v of t. So again, know the difference between average velocity with respect to position, average velocity if I have velocity itself. Instantaneous velocity is velocity at that exact moment, which is my derivative, and positive acceleration tells me velocity is increasing, negative acceleration tells me velocity is decreasing, speed is the absolute value of velocity, and total distance traveled is simply the definite integral of the absolute value of velocity. And that's all I've got for you. We'll continue on in 8.2 talking about area and the integral.